So from smartphones to supercomputers, today computers are heterogeneous systems. They may contain all kinds of devices from FPGAs to discrete GPU cards. And clearly we need good tools to extract the computing power from all these systems. Several frameworks exist that help with heterogeneous programming. Most commonly known are CUDA, OpenCL, and now becoming more popular, OpenACC. And there are, of course, many domain-specific languages that are built on top of CUDA or OpenCL. However, programming heterogeneous systems remains difficult. And here are some things that I would like to see that I think would make life easier if they would exist. So computational kernels normally exist as part of a bigger application. And as such, I think it makes sense for them to be in the same source code. So I don't need separate compilers or something like that. Now, the language for computational kernel should be expressive. I don't want to be restricted by the language in terms of what I can implement on a device. Now, as I said, these kernels are usually part of a bigger system, and so it makes sense to use the same variables inside the computational kernels implicitly. OpenCL, for example, or even CUDA to some degree, make programmers write a lot of boilerplate code, and I would like to avoid having to do that. Now, it's usually a challenge to tune an application for specific hardware, and the more tools can assist with that or even completely automate that, the better. Finally, once I have an application running on specific hardware, I don't want to repeat all the tuning and optimizing for new hardware. So tools should help me with portability. With all this in mind, I started designing and implementing CLOP, which is a platform for heterogeneous programming. It's essentially it's an external language. It has its own syntax, but it doesn't exist outside of a deprogramming language, which is its host. CLOP implements most of the OpenCL syntax, and so almost everything that can be implemented in OpenCL can also be implemented in CLOP. Now, CLOP compiler manages the device buffers and data transfers for devices automatically, so that the programmer doesn't need to take care of it themselves. CLOP contains some high-level constructs and convenient types that make it easier to program for heterogeneous system, and the code becomes more compact. The way CLOP compiler operates, it's all done at compile time, so there's no additional runtime overhead, as usually the case with embedded DSLs, for example. And as I said, CLOP exists on top of the D language, and so D is not very popular yet, so I think it would be a good idea to give a short course on some of the D features. One of the important features that CLOP relies on is string mixins. Essentially, so here, for example, I have a mixin of some expression. Essentially, mixin takes a parameter which can be almost arbitrary expression in D language. The only constraint that this expression evaluates to constant string at compile time. So here, S and V will be concatenated, and the result of that concatenation will be another string, which is then mixed in as if it was a valid D statement. An interesting thing that mixins can be nested. So the result of mixing in one expression can contain another mixin. And in this particular example, this leads to next interesting feature of D language, compile time function execution. So again, at line 5, I have a mixin, and the parameter to that mixin is a result of calling function format. So when this function is called, and actually it's called at compile time. So decompiler must have almost full interpreter of D language. So that interpreter will execute format at compile time, and the result of executing it will be another string which contains characters 1 and 0. And when this string is mixed in, I will have a declaration of variable x initialized to integer value 10. And just to remind you, I started with mixing in concatenation of two strings s and v. Another interesting feature of D, D actually has very rich compile time reflection facilities. So in this rather complicated example, a few things are interesting. So for example, traits. There are multiple traits that decompiler implement. This particular trait, I can access all the members of a struct pattern. So traits all members pattern will be expanded at compile time to a list of strings which contain names of all the members of the struct: method, generate, diagonal, and horizontal. And then I can iterate over all these strings at compile time. So when this, the next statement is, when the statement at line 16 is compiled, decompiler will create an object of struct pattern initialized with string horizontal. And then it will invoke method generate on it. And when this method is executed at compile time, statement at line 6 eventually will be executed, specifically when variable m will contain string, will point to string horizontal. And then the second part of this if statement will be evaluated, and I will use another trait, getMember, to extract the member with the name horizontal from this object. And then I will take, I will query the type of that entity. And the type will be callable function. So this is callable will be true, and then string will be returned, and this will result in a certain statement in this program. So CLOP stands for OpenCL optimized. It has basically two meanings. One is the optimized use of OpenCL, so it's much more efficient to, it should be more efficient to program with CLOP than with direct OpenCL. But then another meaning is that CLOP will eventually generate optimized OpenCL code. In order to introduce CLOP, I will use a concrete example, specifically an implementation of Needleman-Wunsch algorithm frequently used in bioinformatics. So this part of the code is essentially CLOP fragment, and it's embedded in a definition of class written in D language. So this is the class. I begin with declaring two multidimensional arrays. ND array is a type provided by CLOP runtime library. When objects of this class are created, we can specify the sizes of dimensions. And depending on the number of parameters to the constructor, it will be either one-dimensional, two-dimensional, or three-dimensional array. Here, I create two arrays of two dimensions, and the sizes of each dimension are rows and values of variables rows and cols. Internally, this ND array represented as a one-dimensional array suitable to be used on devices like GPUs. And then to invoke the CLOP compiler, I will use this construct, mixin compile. It will take the string contained as a parameter, and it will generate OpenCL API calls and the OpenCL kernel corresponding to this code. So the main construct of CLOP is ND-range statement. ND-range statement defines an index space. For example, here, if rows and cols were equal to 8, it will be two-dimensional index space size of size 8 by 8. And there are two index variables, R that runs from 1 to rows and C that runs from 1 to cols. In addition to the index space, I can specify synchronization pattern, how this index space will be used. So the word anti-diagonal means that the entire index space will be divided into anti-diagonals like this. And the code in the compiled statement of the ND range will be executed for each anti-diagonal in parallel. Now, the compilation of CLOP goes like this. So there's a host application written in D language, and it contains CLOP code embedded in it. that application is compiled by host compiler, which is D language compiler, and D compiler invokes CLOP compiler through compile time function execution mechanism. It links the application with the runtime library, and as a result, there is an executable program in the native code of the machine that this system runs on. And that program will contain embedded OpenCL code. The compilation proceeds in stages. So I begin with the CLOP fragment source, as I showed with needle and launch example. And the first thing that CLOP compiler does, it generates two compile time values. One is basically just the source of the CLOP fragment, and the second is the abstract syntax tree generated from that source. This abstract syntax tree is passed as a parameter to the next stage, along with the name of the file that contains this CLOP fragment and the line number where that CLOP fragment was located. This is for proper diagnostic from the CLOP compiler. Then stage one will analyze this AST, and it will extract the types of all the variables that are not bound inside CLOP fragment, but are declared in the main application. Along with the types, there will be another piece of information, array of names of those parameters, so that the next stage will be able to generate all the necessary parameters for the generated OpenCL kernel and buffers and data movements related to this data. So the final result will be this block of D code, which will be mixed into the main application, and that D code contains all the necessary OpenCL API calls and the generated OpenCL kernel. And just to compare the size of the code, so on the left side, this is needle and launch application written in CLOP, and on the right side, the same program written in OpenCL manually, although it contains several optimizations. So I mentioned that CLOP is also supposed to generate optimized OpenCL code, and this is mostly for future work. So for example, with this needle and launch example, instead of going over the index space in anti-diagonals, it would be nice to specify, to split the space into tiles, for example, of rhomboid shape. And traversing this index space in tiles would be much more efficient. So if CLOP compiler could generate code that does this automatically, it would be very helpful. Now, another feature to consider is task pipelining. So currently, CLOP compiler will generate data transfers before and after the kernel, depending on how the data is read and written. And sometimes it's not necessary. Often kernels generate data that can stay on device to be used by next kernel. And so it would be nice to construct pipelines of tasks. And the language needs to be extended for the CLOP compiler to understand this. And that concludes my presentation. Thank you for your attention.